Hi there. So there's a really great live stream out there called Navigating Large Code Bases, and it kind of walks you through how you can deal with Unreal Engine at the source code level. They've got a resource guide as well, which has a collection of lectures. I've converted them from PowerPoint to PDF, and I'll provide a link in the description for the files and the URLs that I show here. So no worries on that front. Anyway, I was reading through the Cloud Shader walkthrough, and surprise, surprise, it walks you through the building of a material that renders a volumetric cloud using ray marching. So I thought it was really interesting and would make a great tutorial. So I'm going to try and walk you through the same set of slides here, but rather than doing it all in code, we're going to use the material editor whenever possible. So let's get started with that. Create a new material. And one of the first things you'll want to do is make this an unlit material, because we're just going to be setting the emissive color, and later on we will set the opacity, so we'll make it translucent as well. Now, the absolute world position returns the point on the surface of this object. So if we plug this into the emissive color, well, you can see the various segmented colors, but it's also got a lot of bloom, so we can saturate this, which will clamp it in a 0 to 1 space. And then if we were to take a sphere, place it at the origin, and take our material, if you've done any kind of shader development before, you've probably seen this. But as we move our object around, the material doesn't go with it, and that's because it's in world space. So in order to change that, what we can do is factor in the object position. If we get the direction vector between the two, apply that. Now when we move the object, the material goes with it. Okay, that is cool. Now, we're just going to disconnect that. So you know what this does now, and you know what this does. And we're just going to build up the logic here and just kind of break down nodes as we go. So the next thing to do would be to convert this to a quad. Now, if you don't see it, you need to rotate it into view. And with this quad, what we're going to do is we're going to generate a sphere mask. Now, there are a couple of ways you could do that. One is through pure math, and that would be, one second, let me find the code in my other editor here, but we're going to use the dot product in this. Now, you've probably used the dot product before to find the angle between two vectors, but in this case, we're going to take the dot product of the same vector. So what does that mean? How is that possible? Well, there's a great video, which I will post in the description, giving a breakdown of what this means. And he walks through a couple of proofs here. But in summary, to take the dot product of the same vector, you end up with the magnitude of that vector squared. So really, that's just a scalar value at distance. And what we can do is, if I plug this directly in to saturate, here, I'll move this over. It's just pure white. But actually, if we multiply this and we multiply it to reduce it by, let's say, that much, we can see a sphere mask here. I'll get rid of this grid as well. Now, this is just I don't like magic numbers like this. So what we're going to do is we're going to calculate the sphere mask so it kind of fits within the quad here. But before we do that, let's actually have a look at how we could do this using an existing node, and that would be with the sphere mask node. And it's much easier to use. So A takes A and a B, so this will be A and B. The radius is 256. You can set it to an arbitrary 100, and you can see right there we have a sphere mask. You can also set the hardness, so like maybe like a 0.1 here, give it a little soft edge. And the hardness is like the smooth step, the transition between the edge and the inner sphere mask. So that was interesting. And what we want to do, the reason we want a sphere mask is we're going to put the cloud rendering inside of this sphere mask. So before we do that, let's back things up a bit and tackle how do we actually fit a sphere mask within the bounds of this rectangle here, this square. So the way we can do that is we need so for a unit square, from the center to the corner point, if you take the square root of 0.5, you can get that. Now, I am not a math expert by any means. I can barely add two numbers together, so if I'm telling you something wrong, please correct me. Now, we'll take the object radius here, and we will take that and multiply it by this to get that distance. And then, actually, let's disconnect this dot product. And we're going to take the, if I could type, no, I want divide. So with our world position minus our object position, we're going to divide this vector, our position, by the object radius that has been multiplied from this distance between the corner and the center here. And from that, with this position, we can do our dot product. And let's feed this into the saturate. And it may look like it's not actually working, but I think it's because the whiteness is very hard to see the difference. So if I do a 1 minus here and invert it, hopefully we'll see a sphere that runs to the very edges of this quad. Now, instead of doing that, we can also use a smooth step. Now, a smooth step function is basically an S-shaped curve function, and it handles the transition between two values. It steps between them. And we can have a nice kind of faded transition or a harsh one. And there we have it. Now, there's a video that I'm going to link to, done by The Art of Code. He talks about how to build a smooth step function using a graphing calculator. It's a really great video. You should totally watch that. And there we go. So at the end of this, we basically have a sphere mask that fits within our quad here. And what I want to do next is I want to render noise and then multiply that noise by the sphere mask, so only the noise happens within this sphere. So to generate noise, there is a node for that. And the values that I'm going to use in this are completely arbitrary, but I'm going to match the values shown in the PowerPoint or PDF, just so we're on the same page. But again, they're completely arbitrary. Now this takes the position which we were talking about calculating over here before we do the dot on that vector, and then we will take this and let's just plug it into the emissive color here, and you can see the noise. Now if we take this and we simply multiply it by the mask, we should have some noise inside of a sphere. And there you go. Cool. So next up, cloud density. So we basically want to, for this particular noise function here, we're going to need to run it inside of a loop. Now you can create a material function, but then you can't use, there is no for loop in here. So we're going to have to use a custom node. And I guess we can, I don't know if I want to continue to saturate it here. I guess I could, but whatever, we'll bypass it for now. So with this custom node here, right now the code returns 1, so pure white. And it's returning, oops, if I click on it, it's returning a float 3 color. So for the actual code, let me bring it up here. I started typing a bit of it. Basically, we're going to create a structure that is called cloud. I create an instance of that struct, and then I call the function on it called density. This density function returns a float, and currently it just returns 1.0 based on the position that's passed into it. And then I simply build a color using that value to create a grayscale. So if I copy and paste this, we should see no difference to the color. It should still be white. It doesn't know what P is. That's because we need to add that parameter input. So our position. And there we go. So we're all set up to start rendering a cloud density, I should say. But really, it's going to be this noise function inside of the custom HLSL, so we can use it in a for loop when we get to the ray marching section. So let me just copy and paste what I have in here, so you don't have to sit here and watch me type. Oops, we don't need the function name again. So it starts off by creating a mask using the smooth step function, using the dot of the position vector there again. So exact same code that we've been seeing up to this point, and it's saturated or clamped from 0 to 1. And then the noise function uses that same material expression, that noise node, and it uses all of the same parameters that I had before. And now, how did I discover, this is a Boolean, an integer, or a float? Let me open up Visual Studio. And it doesn't matter what project it is. It could even be Unreal Engine. It's just a particular project I'm working on. So we do a search for, oops, there we go, come on. So if we do a search for material expression node, we'll search the entire code base, and then here we can see it's contained in this USH. It's the Unreal Shader header, and you can see the function and then all of the parameters for this, and then the particular types, whether it's an int, a bool, or a float. So that's how I determined that. Then once we have the noise, we multiply the mask by the noise to return the exact same thing. So with this code here, I'll just copy paste it. We should have a similar result to our previous experiment. And there we go. So exact same thing. That's really all we wanted. But again, now we have it in custom HLSL, and we can use it in a ray marching loop, which is going to be next. So let's actually break down how to do some basic ray marching. So what we're going to need is we're going to need a camera vector, and we will invert this, multiply it by a -1 to flip it. And with this, I'll just copy this custom node here, and we'll get rid of all this code. Set it to 1 white and wire it up. And I'll move the position. Actually, no, we still need the position. And what we're going to need here is the camera vector. Now, for ray marching, what you do is you cast a ray from the camera position here into the scene. And that is, I typically call it the, let's add a new input here. Call it RD for the ray direction. Oops, and come on, I can click the node. There we go. So for this, we're going to have a for loop, and it's going to look like this. So we can see it here with some syntax highlighting. So define a maximum number of steps, how many times to go in the for loop here. And then I have a distance value that we accumulate with each step. So if it's, as soon as it hits the maximum number of steps, it's going to break out of the loop. And if it happens to go beyond this distance of 1, it'll break out as well. And through each step, we basically add and assign to this position. So we increment the position with every iteration through this loop, the array direction divided by the maximum number of steps. So some small little amount here, and then the distance here, which I'm basically use as a color that is returned, a grayscale color here. We do the same thing. We just do a 1 over the max steps and add that small little increment. So if we copy this into our remarching shader here, you can see we've got these circular patterns here, which is nice. So we've got slices in our onion. And if you wanted to see, 4 of them, you change that to 4, and there you go. You can see 4. Actually, if we make this less than 1, kind of invert it, and it's black here, but you can see on the edge, you can see the side of the sphere. It's a little tough to see with 4. Let me bump it up to 8. There you go. But I want it the other way around. And there we go. So now what we're going to do is we're going to use this distance field here to determine basically how to shade the sphere eventually, or sorry, the noise or clouds within there. So the last step for this video is kind of getting to, I think, I walk you through up to this point here. Beyond that is volumetric lighting, which you can have a look at with the Shader Bits blog, Ryan Brucks. Once you get to this point, you can start, I think it's a good jumping off point or springboard into this article. You can wire up the volumetric lighting for this as well. But we're not going there for today's lesson. We're just going to go right here to just hooking up our cloud density function to just kind of get this orb with a shady interior. And to do that, we are going to need another custom node here, but this time it's going to be a float 4, because we're going to return opacity as well, and I'll show you the difference there. In addition to that, we're going to need a color, and I will call this input albedo or albedo, however you want to pronounce it. And we'll just give it a bluish color. So I'll just copy and paste some of these nodes again. We'll just move it down here. Move this down. So with our position here and our redirection, we will hook up the emissive color initially. And the final bit of code is basically just a slight alteration to our existing code here. So we still have our maximum number of steps, and you can see the cloud structure here. But this time what we're doing is we're declaring a float 4 color variable that we're going to return. And inside of the for loop this time, we do a couple of things. One is we multiply the array direction by 2, and that's because I'm going to switch this to a sphere, and a unit sphere is 1, so we need twice that amount. And then, so how dark is the noise here? So I take the cloud density here for the position, and we multiply it against the particular color to scale it. And this would be the alpha. And then with that temporary color variable, we do a 1 minus to invert it and multiply this local color variable by it to get this final color that we accumulate over time. And if we run this, it complains about cannot implicitly convert from float 3 to float 4. Yes, that's because I haven't pasted the new code in. And I'm not sure why, but this, as soon as I start doing this, for some reason, it just launches a whole bunch of shader tasks, compiler workers, and eventually it will go. I'm not sure why there's such a significant difference between this and the last bit of code. As you can see, it takes quite a while. And there you have it. We have this volumetric ray marcher, at least the basics of one. And you could create a cool looking marble here. So as I said before, the next thing to do would be volumetric lighting on this and give this a Fresnel effect, and you could have something pretty cool. Anyway, that's it for now. I'll talk to you later.